Let's prove this identity, this trigonometric identity, where we have the sine of 2m of x multiplied by 2 to the 2m equal to this summation, which contains some cosines and some binomial coefficients, and also we have another binomial coefficient here. The easiest way to prove this equation is the following. So if we use the Euler identity for the sine of x, which is e to the ix minus e to the minus ix divided by 2I. And also if we make use of the binomial theorem, but we will do it in a few steps. First, this is the equation that we will use. Then we will also use the binomial coefficient. But first things first. So let's start with the sine of 2m of x. So we are starting from here, and we are going to prove that the sine of x to the 2m is related to that summation there. So we can rewrite it as this is equal to e to the ix minus e to the minus ix divided by 2I to the power 2m. I can factor out 2I, so I have 1 over 2 to the 2m, and 1 over I to the 2m can be written like this. It is just minus 1 to the power m or minus m here. So why am I saying this? So in principle this should be minus m, but when I have minus 1 to the power m, this is also equal to minus 1 to the power minus m. This is very easy to prove because if I take this to the left hand side, I have minus 1 to the power 2m equal to 1, which is indeed satisfied. So this is of course true. So I can either write minus m or plus m when I have a minus 1 to some power, because it is not really important. Okay, but so I started from 1 over I to the 2m, which is equal to 1 over minus 1 to the m, which is equal to minus 1 to the power minus m, but it is also equal to minus 1 to the power m. So this makes no difference. And then I have to consider e to the ix minus e to the minus ix, and I have to consider some power of this, the power of 2m of this. So how can I express this power? I can use the binomial theorem. The binomial theorem tells me that if I have two numbers, let's say x and y, and I have to raise them to the power, this sum to the power n, this can be written as summation with the index k ranging from 0 to n. Then I have x to the power n, y to the power n minus k, and then I have the binomial coefficient n choose k. So I can write it like this, but I can also write it in a different manner. For example, I can write it like this: y to the power n, x to the power n minus k, because there is symmetry with respect to x and y, so this is not really fundamental. Okay, so this is what we can do. And we have to use this formula to rewrite this expression here. And this is equal to, let me do it below, this is equal to, I have 1 over 2 to the power 2m, then I have minus 1 to the plus or minus m, let's say minus m, and then here I have the summation with the index k going from 0 to 2m, and then I have e to the ikx, so when I raise this term to the kth power, I have e to the ikx, and then I have to raise this term to the power n minus k, and let me first consider this one. I also have the minus, this is also important, but I will consider it later. So I have e to the minus I 2m minus k, so instead of n, here I have 2m, right? And then I have minus 1 to the power, in principle it is 2m minus k, but I also have minus 1 to the power minus m, so I can get rid of this here, and I have to multiply here, and instead of 2m I will just simply write m. So I have m here, and if I want I can also put a plus instead of a minus here. It's not important, as I said, because when I have minus 1 raised to some power, it is also equal to minus 1 raised to some minus that power. In this case we are talking about integers, so there is no problem doing that, right? So I have plus, I can put plus here, okay? Because minus 1 to the minus k is equal to minus 1 to the plus k. And then I also have to consider the binomial coefficient and choose k, but instead of n we have 2m here, so I have 2m choose k, and this is equal to, let me rewrite it. So let me do it here without writing all the entire formula. I can rewrite this product, the product between these two exponentials, like this: e to the minus I 2m minus k x, because when I take the multiplication, when I do the multiplication between these two complex exponentials, I simply have to sum the arguments of the complex exponentials, right? So I can rewrite, if I rearrange the terms like this. And now we started from, remember where we started from? We started from the sine of x to the power 2m. So we must have a real number on the left and also on the right. In this case, we are summing complex exponentials, right? So it means that the imaginary part should vanish. It will go to zero when I take all these summations. So if I take the real part of this, it is still equal to the same expression, because I know that the imaginary part will vanish, will have to vanish in order for this expression here to be equal to this one, because that's a real number after all. So I can rewrite this, if I take the real part, 1 over 2 to the power 2m, and then I have sum with the index k ranging from 0 to 2m. Instead of the complex exponential, I can put the cosine of minus 2m minus k x, but since the cosine is an even function, I can also put a plus here. And then I have minus 1 to the power m plus k, 2m choose k. Okay, and now I'm going to do the last few steps, because I'm going to rewrite the summation. I will split the summation into three parts. So I will have 1 over 2 to the power 2m summation from k, sorry, with k ranging from 0 to m minus 1, and then I have this expression here. So let me not write it. I'm not going to write it. It is exactly the same. And then I have plus 1 over 2 to the power 2m within. So in this case, I'm going to rewrite the term where m is equal to k or k is equal to m. So in this case, I'm going to have 1 over 2 to the power 2m, and then I have 2m choose m here, and then I have plus 1 over 2 to the power 2m summation with k going from m plus 1 to 2m of the same expression here. When I consider these two summations, this one and this one, you can see that these summations will contain these terms, the cosine and then minus 1 to the power m plus k, right? And also there is this binomial coefficient, 2m choose k. But if you take a look at those terms, it is quite easy to prove that these two sums are equal. Because, for example, here the cosine will contain these terms. So it will this first summation will contain cosine of 2mx, and then it will also contain cosine of 2m minus 1x, and all the way down to cosine of 2x, because I have 2 times m minus 1, which is 1, so I have 2x. And something similar will occur for this summation here, but instead of a plus sign, I will have a minus sign in the cosines. For example, when I set k equal to m plus 1, I will have cosine of 2x with a minus sign, so minus 2x, and then I will have, when I set k to m plus 2, I will have cosine of minus 4x, and then I will go all the way up to, when I set k equal to 2m, I will have cosine of minus 2mx. But this is equal to the cosine of 2mx. This is equal to the cosine of 4x, and so on and so forth. So these cosines will be the same, and the same will hold for minus 1 to the power m plus k, because I can change, for example, the sign here in the index k. So for the first sum, minus 1 to the power m plus k will be minus 1 to the power k, and then I will have minus 1 to the power k plus 1, all the way up to minus 1 to the power k plus m minus 1. Whereas for the second summation here, that term will be minus 1 to the power k plus m plus 1. And if I want, I can also change this sign to a minus for the properties of minus 1 to minus 1 raised to some power. So this will be equal to that. And then I will have minus 1 to the power k plus m plus 2. And I can change the signs here. And one of these terms will be equal to one of those. And then when k is equal to 2m, for example, I have minus 1 to the power k plus 2m. But this is equal to minus 1 to the power k, of course, because when I have minus 1 to the power 2m, that's equal to 1. So this will be equal to this, and so on and so forth, right? I mean, this also holds for the binomial coefficient. You can check that these two summations are exactly the same. So what we get is the following. We get that this is equal to twice the summation. So I have 2 the summation time divided by 2 to the power 2m, with the index k going from 0 to m minus 1, and then I have cosine of 2m minus k x minus 1 to the power m plus k, 2m choose k, plus 1 over 2 to the power 2m, 2m choose m, like this. And remember that this is equal to the sign raised to the power 2m of x, right? And when we multiply by 2 to the power 2m, we can get rid of these two terms, and we have a factor of 2 to the power 2m here. If I get rid of this and this, and this is the formula that we get, which is exactly the formula that we wanted to prove here.